Okay, I will continue. So sorry for the interruption, and I was not into this. This was simple introduction to some general kinetic equations. And so we are interested in the long-time behavior of these type of kinetic equations. So the typical behavior is that the transport term drives the process away from the local equilibrium, unless you're in the global equilibrium, and the collision term tries to get the, which have a dissipative effect and tries to drive the system to the equilibrium. Then what we are interested in is to estimate the effect of dissipative part on the space variable. So this is called the hypocoercivity. So more precisely, we would like to find a time-independent solution, and our solution to our kinetic equation f of f sub t converges to this time-independent solution as time goes to infinity. So more precisely, we would like to prove an inequality of this type, where we are also interested in quantifying this constant and this function of time beta of t here. So if we can prove such an inequality for our generic kinetic equation, then it is said to be hypocoercive in the appropriate distance, which will be specified later. So if p of t, beta of t is an exponential function, then we have geometric or exponential convergence, or if it's a polynomial function, then we will have the subgeometric convergence. So today what we are interested in is some certain probabilistic techniques to show these type of inequalities, and they are associated to the ergodicity of Markov processes. So there are two classical approaches to show the ergodicity of Markov processes, according to this, citing this paper here. And one of them is Poincare type inequalities, where you need to have integral bounds on the generator of the system. And the second one is Lyapunov function-based methods, where you find an appropriate Lyapunov function and try to prove some type of inequality on the generator of the process. So what we are interested in today is the second approach. And so, as I said, we will associate this kinetic equation to a Markov process, more precisely, continuous time Markov process. And we know that continuous time Markov processes, or in general Markov processes, can be defined by means of transition probabilities. In the case that it's a continuous time Markov processes, we have family of transition probability functions, via which we can define a linear mass-preserving, positivity-preserving semigroup. So just to mention our setting a bit, PT of ZE here is a transition probability functions for all t greater than or equal to 0. This is defined. And here, Z is in the phase space, and E is a Borel cell, and we will take the measurable space where to be like everything to nice perfectly. Z is a Polish space. And curly M of Z will be the space of finite measures. And well, it showed up in the previous slide, but curly P of Z is this space of probability measures. So we can, by using these continuous time Markov processes, we can define a Markov semigroup, which is a linear positivity preserving and mass preserving semigroup. How do we define it? This Markov semigroup acts on the finite measures in the following sense. Here you see the transition probabilities. And also its dual semigroup acts on the measurable functions. In the following way. So by using these inequalities, we can associate this semigroup like related to the kinetic equation through the continuous time Markov process. So in this setting, S sub t of f0 will be the solution of our kinetic equation at time t with an initial data f sub 0. So in the sense of the stationary state or time-independent solution, it will be ST F infinity is equal to F infinity. So it is also in the context of Markov processes is called invariant measures. These are all I refer to always all the same things. You use them interchangeably. So let's go to a bit of history of Paris-type theorems. So the basic, original ideas go back to the Douglas paper in 1940, where he showed that for a Markov chain, if you can prove the transition probabilities are there is a positive lower bound for transition probabilities, then this Markov chain admits a mixing property, which means it will have an invariant measure. And in 1956, Paris, by interpolating these ideas, he gave a conditions for an existence and uniqueness of an equilibrium state or invariant measure for a Markov process. And in a couple of series of papers in 90s, Main and Tweedy pushed it to show the exponential convergence, how we can show an exponential convergence using these previous ideas. And what is here somehow, I mean, these theorems are known in probability community a lot, but what made it famous in the PD community is this paper of Martin Herrer and Jonathan Mattingly. So they showed how one can obtain quantitative convergence rate once hypotheses on the theorems are satisfied quantitatively. And they also gave an alternative proof using mass transport distances. So the previous proofs were based on probabilistic terms and base, let's say. And there is also recently a paper by Jose Maniso and Stefan Mishner. They provided yet another alternative proof for proof using just PD arguments, semi-group arguments, and some interpolation arguments. And I would like to make an advertisement. If today I will skip the proofs of these theorems, I will just state them. If you are interested in the proofs, you can come to again in these seminars in May 17th, because I will be talking about the particular this paper. And let's get to the statements. So, or before the statements, what they mean. So it means that if we can prove for a Markov process, if we can, okay, maybe it's better to graphically represent. In the case that we have discrete state space, for example, this is our state space, and these are the different states. And if I can prove if I start any arbitrary place, state in the state space, let's say this, if I can prove probability of transitioning from this arbitrary initial point to any point in the state space, let's say this one, if the probability of transition from here to here is positive, then after some time I visit all the states. So I can say that then there is an invariant measure for this Markov process. So it's in the discrete setting. And sometimes this state space here is this one. Sometimes the state space is not bounded. In that case, it is difficult to prove a uniform bound for transition probabilities. So what we do is that we can prove still such a uniform positive lower bound in the central state space, and for the states remaining outside this set, we, by means of finding the appropriate Lyapunov function, we can show that the process converge to this subset often enough, and how strong this Lyapunov function and the inequality on this Lyapunov function depends on the rate of convergence. So if we can prove a stronger Lyapunov inequality, then our convergence will be exponential. If it's a big type of Lyapunov inequality, then the convergence will be sub-exponential or sub-geometric algebraic. So sometimes this uniform, this first condition is referred to as uniform mixing property, or there are many names. And also the second one is geometric drift condition or post-Lyapunov condition used often. And so the simplest case is Dublin's theorem, where you can find a uniform positive lower bound for these transition probabilities. So it translates as verifying this type of condition, where finding some constant and some some probability measure and some time tau, and the solution after tau time will be bigger than a probability distribution times this constant. So if you can verify this type of condition on the state space uniformly, then Dublin's theorem gives the exponential existence of a unique stationary states and exponential convergence towards this state in the total variation norms. Of course, it's the usual norm when we are using measures between two measures. And then, as I said, you can quantify these constants here. They are given in terms of the conditioned hypothesis here. So when you cannot prove this type of inequality uniformly over the whole space, then you get to Harris's theorem here. You have a similar condition like the Dublin's condition here. Here is minorization condition. And this is only valid, you see, for all mu in probability distribution in some set. This set is defined, how big this set is defined by the Lyapunov inequality we need to prove in the first hypothesis. So this is here, I wrote the kinetic equation like this in the beginning. So what I show as that F, so it will be C minus T F. So N star is the formal adjoint of my kinetic equation, the operator governing the kinetic equation. So, and I would like to find some Lyapunov function which verifies this type of inequality. So if I can show these two hypotheses, then similarly I can get to an exponential convergence to equilibrium. Okay, here it's complicated, but you can also quantify this lambda and C. I did not write it, I skipped it. And then, as I said, if you cannot prove this type of strong inequality, then, but you can prove sometimes still the weaker version of it, then you get to algebraic or sub-exponential convergence. So it looks a bit horrible, but just I would like to convey the idea. So first we look at the minorization condition. It is the same as before, which is valid in a set, and this set is for every positive number we can define this set, and the Lyapunov function is now has the compact level sublevel set. So B will be the Lyapunov function taking the function inside, which is defined as a measurable function. And if we can show this type of inequality in this case, we can show that this total variation, there exists a unique stationary state which will satisfy this inequality, and we will have certain bounds on it. There's some complicated terms, but yeah, these things are not very important at this point. But here, what is different is also that we assume that the semigroup has a feather property. That means it maps the space of bounded measurable functions to the space of continuous functions. So this is, I'm using the versions of these theorems in the last paper of Jose Canizo and Stefan Michler, so that they require this condition to be able to show the proof with the semigroup arguments. So in our cases, like the examples I will show, this is always satisfied. So it's not very important, but it's a difference than the other two theorems. So okay, and next, so okay, before saying it, I skipped maybe references. So I wrote recently a review concerning the quantitative hypocoercivity results using these type of arguments, and in that I cited here. You can find all the references that I maybe forgot to mention, and where I investigated these these kinetic equations. So in the gas theory, we look at the linear BGK, linear Boltzmann and linear degenerate Boltzmann equations. Here, this work is by Joe Evans and Ivan Komenov. And here also a result on linear kinetic focal line equation by Chuki Kao. And there are also results using this type of arguments showing the collisionless gas, meaning the free transport equation with some Maxwell boundary conditions and Cherginian-Gauss boundary conditions by Armand. And finally, again, Joe and Angelique, they show the existence of a nonequilibrium stationary state or nonlinear BGK equation with posed on an interval by again using these Harris type theorems. And then I also revised these two biological models. First one is the Raman-Tumble equation. It's a work by Joe and myself. And there is also the Fitzhugh-Nahuma equation for interacting neuron populations. It's a work by, again, Kao. So, yeah, today what I'm going to try to mention, I guess I will not have enough time actually, but I wanted to do only like the linear BGK equation and maybe some of Raman-Tumble and Fitzhugh-Nahuma. Probably I will not have time for us to. So let's get to the linear BGK equations. It's very simple. I just want to show this as an example, like how we can apply these type of theorems on this equation. So how we define it is, here we have the transport term with the free transport and the with the confining potential, here the external force. And on the right-hand side, we have this operator where I define this part as the C plus, collision plus, which M is the Maxwellian velocity distribution. So given by, okay, this is here, like this in dimension D. And what is shown already about this equation is that it converges to some equilibrium, which is given by the Maxwellian velocity distribution. So when X is posed in torus, we will not have the confining potential, confining term here. Then equilibrium will be only the Maxwellian velocity distribution. And for X posed in RD, and the confining potential is at least quadratic, then we will have exponential convergence. And for, again, X in RD, then the confining potential is sub-exponential, then sub-quadratic, sorry, we will have the sub-exponential convergence. So I will try to show how we can, try to explain how we can show these things. So just to write out the theorem, it looks horrible, but it's not very, very important. So we have the solution to our linear BGK equation, and suppose that there are three regimes. First one is when X is in torus, and there is no confining potential, obviously. And the second one, when X is posed in RD, and the confining potential is satisfying this inequality here, which means it is quadratic. And then in this case, we can find exponential convergence to equilibrium, unique equilibrium. And in the first case, where the equation posed on torus are the norm is weighted total variation distance. And in the first case, it's just the total variation distance. So weight is just 1. In the second case, we can give this. We get the result in this wave function, which I will explain where it comes from. H is the total energy of the system. So in the third regime, where we have the equation posed in RD, but the confining potential is sub-quadratic, size in between 0 and 1. And then in this case, we can find this type of bound for our unique equilibrium. So for the first case, where the equation posed on torus, so we can use Dublin's theorem, so it is easy to verify this uniform lower bound all over the space. So how do we do that? I will first talk a bit about the general strategy here. First, we write the equation, only the transport part and this positive F part. So just remember that we had this part for the equation, right? I'm just taking the F here on the left-hand side. In the case of torus, we don't have the confined potential here. And I show these solutions. I associate this equation with a semigroup, which is defined, which is shown as TT. And the semigroup associated to the whole equation is always S sub T. By using like Duhamel's formula, right, treating the collision term as a source for this equation, we can get this following bound. This is kind of classical. And our strategy is to, like, what we want to do is to find a bound for this this action of the semigroup to a measure. And first of all, we take a Dirac measure initial data, and we know that our semigroup is Markov. We can later extend it to any probability measure. So what we want to do, as I said, just try to find both bounds for the action of this collision operator and the transport operator separately on a measure. So first one is the bound for the collision operator. So what this inequality means is that the jump operator allows you to jump from any small velocity with a predetermined velocity. So you are allowed to jump to any small velocity. And this, the second lemma concerns the bound on the transport part. This says that when you start from a ball of radius r with any point with a small velocity, which you get from the collision part, you know the starting velocity, you can cover any part of this ball. So this is given by this type of inequality. So it's a bit technical, but as an idea, it's very, very simple. So combining these two bounds, you can at the end get a bound for the equation, for the semigroup governing the equation, which is quantitative. I just wrote these numbers just to show that this is quantitative, so that you can really plug these into the C and lambda of on the theorem, and then you can get how fast the convergence is. So now this was for the equation which is posed on torus. Now we are in RD. So in this case, we cannot prove this bound uniformly. Then what do? We just try to show that this process will converge to some part where we can prove positivity condition. So the Foster-Lyapunov condition, in that case, we can easily verify that this Lyapunov function satisfies the inequality on the adjoint of the equation. This and inequality is on the adjoint of this. Let's start. So how do we find this form of this type of Lyapunov function? It is that we guess it a bit, actually, which it will involve the energy of the function, and also we know which type of convergence we will get. We compute these terms separately, the action of these terms on the collision and transport, the adjoints of collision and transport operators. So this, you compute the action of this, or this, for example, x squared is one term, or xv term here afterwards, and v squared term, it's not. So anyway, this, for example, 0, this doesn't, collision part does not act on velocity. So that by combining these actions, you can get to the final form of this Lyapunov function. And for the minorization condition, now the particles do not follow free transport equation. We have also, like, their trajectories are refracted a bit because we also have the confining potential or external force acting on that. So you need to still track the characteristics of the process, but it will be a bit involving. So first you write the, you consider this this ODE and write the solutions to this, and then you try to form an interpolation between these two solutions of these two characteristic problems, and where with the epsilon is equal to 0, and by already when epsilon is equal to 0 the solution of this characteristic, like the bounds on these characteristics. Then by interpolating, you try to get an estimate on the presence of a confining potential. So I again did not skip the details, but it's also like kind of computations. Like as an idea, it's not very difficult. So then combining these 2 points, you obtain the result for the exponential convergence for the linear BGK equation posed in whole space with quadratic potential. For this subquadratic potential, the Foster-Lyapunov condition is, for minorization condition, sorry, is the same. And for Foster-Lyapunov condition, the functional you can get is of this form. So it is, in general, when you try to apply the subgeometric version of this Harris's theorem, the functionals you used are like very similar to this form. So you see it gives you the vast algebraic rate where in the theorem it's also mentioned. So this is a bit maybe fast, but this is the story about the linear BGK equation. So maybe very briefly, I will try to show run and thumb and fix as well. So first we probably, Joe at some point talked about this, was run and thumb process. It is the proposed way of movement for bacteria under the effect of chemical stimulus. So they go free transported, like they go straight lines with constant speed, like following the free transport equations. And then they randomly tumble, they change their direction with a bias towards the chemotactic substance. Then again towards that chemical, they go against straight lines. So they form like this type of movement. So the equation is given, it's as follows. Here you see the transport part as usual in the first generic kinetic equation I showed, and the confinement part, this collision part is a bit different. Where here this is the tumbling frequency, and here is the turning kernel, like describing the probability of changing from v speed v to v prime. And again, the initial conditions here are velocity space is simply a ball which with radius 1, no, with radius v0, so that this will be 1. And so what you observe in long time, the bacteria aggregates towards the source of food or chemotactic substance. So again, the F is the probability density of finding bacteria with position x, velocity v. And as I said, this lambda is the tumbling rate, and which the probability of tumbling happens in a short time interval delta t is given by this tumbling rate times the time and some expiry terms. And here m is this quantity where capital M is the external signal, which is the log of the chemoattractant density. So it looks a bit complicated. S of x is the chemoattractant density, and log of S is the external signal for my equation. So again, this kappa is the probability distribution from changing velocity from v to v prime. So in this context, this is the small introduction to an ensemble, and where we have also fixed with Nagumo, which is describing the interactive dynamics of interacting neurons. Here they are structured with instead of position and velocity with adaptation variable x and voltage variable v, where A and B are different potentials. So this is also some celebrated model, like simplified version of Huxley model for neuron interactions. So I just want to point out the difference between these kinetic equations coming from biological processes with the kinetic equations arising in gas theory. So if we look at, for example, the Run-Ensemble equation and the BGK equation together, we see that they look very similar. And one difference is that the confinement mechanism. So here in the BGK, we saw that confinement comes from the external force and confining potential, whereas in the Run-Ensemble equation, confinement is induced via the internal dynamics. So in this case, it is the bias of bacteria towards the gradient of chemoattractive density. So this is one difference. If we look at, for example, Fitzhugh-Nagumo versus kinetic focal Planck equation, which I did not mention today, but many of you know how it looks like probably. Here, what's different is that they look very similar, and also in this case, their confinement mechanism is also not very far away from each other, because this intrinsic noise in the Fitzhugh-Nagumo acts only on the voltage variables, not in the adaptation variable. So it's similar to the case that the collision term acts only on the velocity for the kinetic equations, let's say. So this is the difference, one difference. But another important difference is that for this kinetic focal Planck, linear kinetic focal Planck, and also linear BGK, we can write their stationary states explicitly, right? For the kinetic equations coming from the biological processes, this is all, like, most of the time not possible. You don't know how their equilibrium state looks like. So this sometimes poses problems when you want to use classical hypocoercivity techniques due to Vienna and other people. For example, in the case where there is by Jean Dogo, Noah, and Schmeiser 2015 paper, they generalized somehow the Viennese hypocoercivity method, and the condition there for F infinity to be a stationary solution for a kinetic equation is that it should lie in the intersection of these kernels of these two operators. So this is when you have this type of condition, then using these type of techniques, you can prove the exponential convergence or hypocoercivity. But in the case of Run-Ensemble, this condition does not apply. So it is difficult to use this type of techniques. Then you need some alternative way of showing the hypocoercivity. And yeah, one motivation is that Harris's theorem gives, because as we see in the statements, we do not need to know any information beforehand about the shape of the state for to be able to use Harris's theorem. Whereas for the classical hypocoercivity techniques, it's often these quantitative inequalities are in the norms, H1 or L2 norms, which are weighted with the inverse of your stationary distribution. And this is in the case of these models, it's very difficult to be able to get to these type of inequalities. Okay, so I also included the results, but today I'm not going to mention them probably, because it's also very similar to the linear BGK case, just that there are some differences because of the terms and how the equation appears. And yeah, so it is. So in this paper, we are able to show the under suitable assumptions. There exists a unique stationary state for the Run-Ensemble equation, and the exponential convergence towards it. And the importance is that we could generalize the existing results to arbitrary dimension from the other results, like the previous results, are either in dimension 1 or dimension 2, sometimes dimension 3 with special assumptions. Here the key point is that we get it in arbitrary dimension. Yeah, so I also wanted to write the main result on the fixed probability equation by Kao. Here also similarly he could improve existing results in this equation, where he could show exponential convergence to equilibrium. Yeah, so this, yeah, the like previous result in this paper in dimension 2. Right now, I guess up to my knowledge, this is the most general result of this type of equation. And yeah, also one motivation I wanted to talk to you a bit about is that it is possible to it's possible to use Harris's theorem to show existence of non-equilibrium steady states, or you can extend it to use to show the existence of stationary state for nonlinear equation by using some interpolation argument and using the inequalities for the linear case. So this is another motivation to be able to use these type of results, which we also did in our some paper. We considered some nonlinear version of Ramadan equation. And finally, so by using these Harris-type theorems, you get completely constructive proofs, and you can quantify the convergence rates if you want to. Like they're quantifiable, but sometimes it's difficult to really track these constants in these integrals. Like, but in an idea, it is possible. And you obtain the results in weighted total variation distances, which is the usual norm, and you consider the measured initial data, which is a finite measure. And one maybe hopeful direction is that you can use them to show existence of non-explicit stationary states or non-equilibrium stationary state. And yeah, as I said, often the models arising in applied sciences, they don't have explicit stationary states. So that's in that case, it's difficult to use classical hypocoercivity results. So in those cases, Harris's theorem gives hopeful direction. Say, yeah, I think I took so much time. That's all. Sorry. Thank you.
Thank you, Colin, for the great talk. Any questions? You mentioned the nonlinear case at the end. So the nonlinear case is something weakly nonlinear. So the dominant part is the linear part.
Yeah, exactly. It's weakly nonlinear because the idea is to show that by some type of finding fixed point of a nonlinear equation and showing that at the end the equilibrium state for the nonlinear equation is the same as the linear one, and use some type of perturbation to show that just weakly.
I have a related question to me. So in the linear case, exponential convergence, how does it depend on the, so that was fixed, mechanically fixed.
Yes, it's a function of only space, like fixed function of x.
So like what are the conditions of x?
Okay, so
isn't it that s is kind of, I guess, minus a potential?
So it is like the conditions are mostly on m actually, which is log of s. So I will skip that, but I will show you. Yeah, there are some important assumptions there to mention. But here, see, for example, the technical assumptions, just to say that chemoattractant density decreases as you go away. So this is one assumption, and these are all coming from there. So m was log s is the chemoattractant density. And also, you need to have this type of integral bound on this integral, which looks a bit strange initially, but it also corresponds to lower bound in the collision frequency. If you look at the analogy between the kinetic equations and gas theory. So these were the only assumptions we needed. Okay, I say only, but
Yeah, I mean, the reason I asked is that because, yeah, when looking at the sort of convergence to a stationary measure for the runtime, but I guess my first thought would have been, okay, first let's be sure that we converge to a focal plan for the spatial density. I mean, basically, like for long times, I guess, for if you convert enough, I guess you can show that it will separate into a function of X on time and then Australia, or like what here, I guess, the equivalent of and then the equation that you get the spatial density would just look like a focal plan with minus a confining potential. So I would expect the same conditions you were talking about with yeah, when you have the equation with confining potential apply here.
So I don't know that because what it means confining potential here, because there is the.
So what I mean is if you wrote the equation for the spatial density for long enough times, it would just be, I guess, the yeah, time derivative of rho would be a divergence in space of some diffusion coefficient independent of lambda, and then you would have a minus s gradient, no, minus gradient of s times c times rho.
Yeah, so yeah, but okay, so then you say that you couple in basically the s with some type of equation, right? Like
well, s is fixed, right? In this case,
it's in this case it's fixed, but more realistic.
Well, in the more realistic one, then
yeah, exactly. So that's the I guess the hard part when s is coupled with a Poisson type equation, for example. So that was our aim. That's why we get to this the nonlinear regime. We want to see how we can use this Paris, like the inequalities from Paris.
So you don't use at all the long time behavior of the kinetic equation.
You mean for the nonlinear?
Yeah.
Yeah, we wanted to use, but yeah, it was hard.
Is there also a related question? So in the sort of model that you want to get, there is the S or the M are coupled to the bacteria density, right? In which way precisely?
Okay, it's in the so it is a screen Poisson equation, right? On the right hand side, there is the density, bacteria density. So the FDV. Maybe I wrote it something.
But the chemical.
Yeah, see, here this one. That's what you mean.
Okay, so it depends only on the density at time t.
Yes.
It has absolutely no memory of what happened before.
Yeah, but it would be even better, but I guess, but it would be even difficult, right?
Okay, so.
And just this is the next step. Like what we right now do is that, so I showed you this tumbling kernel, the probability distribution changing from velocity v to v prime is uniform in this case, just one. But the realistic case is that it depends on the angle between two velocities. So now we are trying to do that. I don't think there's any result on that. Also, what we considered velocity space was just ball. If we get unbounded velocity space, then we get algebraic rate of convergence. These are the things that we are.
But that's sort of a separate issue from the.
Yes.
From the.
Yeah.
Okay.
Great one. Maybe this is wildly possible, but since Harris's theorem, as far as I understand, is based on ideas from Markov chains and SDEs, and one can prove ergodic theorems for multiplicative SDEs. So instead of just having additive Brownian motion, you have like sigma of x pw.
Okay.
Is it possible to use these ideas for quasi-linear equations? So like non-linear diffusion, even just in velocity or in both? So
it's just that, yeah, I'm not so sure. So I don't know if these equations you mentioned, are they, for example, mass conservative?
Yeah, so your diffusion would be like the divergence of A of F, grad F. A is some function of F, some matrix value function.
Yeah, I don't know, but it's interesting to think about. So
You can have these like multiplicative SEs where the noise gets turned off in some region. But if you have a confining potential
yeah,
that keeps you out of that region, then you have the same like.
Yeah, I think it's also related to, I don't know if I'm understanding correctly, but for example, the GK equation, where you have on the right hand side, the whole collision term multiplied with, I don't know, sigma x, where that sigma can vanish in some part of the domain. So then it is difficult to use like this type of things, but I guess it's maybe related. Yeah, I mean, that's one thing so we were discussing at some point, but yeah, it's nice to think about it. I don't know the answer, but yeah.
Okay, so in the interest of time, maybe we continue the discussion during the coffee break. So thank you again for the talk.